couple of growth and decay applications. And I want you to think back to the compound interest when we were talking about continuous compounding. And we were looking at a formula. Grab the pen. We were looking at A is equal to P times E to the RT, right? So remember, the P represented the money, the initial amount of money, the A, the amount of money after the interest had accrued. R was the rate, and T was time. Well, we're going to use that same formula. We're just going to kind of relabel things when we're talking about growth and decay, but it's the same thing, and it's the same concept. So you'll notice in some of the different word problems that you see, sometimes the letter A is used. And we'll have A is equal to A sub 0 times E to the RT. Sometimes the letter P is used, and it'll be P is equal to P sub 0 is equal to E to the RT. Sometimes Y is used. Those kinds of things are interchangeable. But what remains the same is that this, so in this case, I'm looking at A sub 0, is the initial amount, right? In these problems, we're looking at something that is either growing or decaying. So this is the amount before the growth or decay occurs. A is the amount after the growth or decay has occurred. Again, remember, E is the number. R is the rate at which this is growing. So it's the growth rate if R is positive. And it's the decay rate if R is negative. And we'll look at examples of both. And then T is time. So let's look at a couple of applications and we'll see how this works. Okay, so we have a biologist has 2,611 gram sample of a radioactive substance. Find the mass of the sample after 4 hours if it decreases according to the continuous exponential decay model at a relative rate of 17% per hour. Okay, so we're going to use our exponential model. A is equal to A sub 0 times E to the RT. So let's think about what we're given. Okay, we have this 2611 gram sample of a radioactive substance. That's what we're starting with. So that's our A sub 0. Find the mass of the sample after 4 hours. So A is what we're looking for. We're looking for how much of that sample is present 4 hours after this decay has occurred. So 4 hours, we were just given a time, so T is 4, and we're given that relative rate of decay. So we're given the R, and since it's decaying, it's getting smaller, it's negative. So negative, I'm going to rewrite that as a decimal 0.17. Okay, so again, what we start with goes here, 2611. What we're after this decay has occurred, that amount is what we're looking for. Remember, E is a number, R is negative 0.17, and T is what we're looking for. Oh, no, T is 4. I lied. T is 4. Let me fix that. So T is 4. Okay, so we're just going to plug this side of the equation into the calculator. So I brought the Alex calculator up so we could see exactly how to do this. And so really you can plug in exactly what you're looking at. So we're going to do, okay, 22611 times E. So I'm going to hit E to the X. And then in the exponent, we'll go negative 0.17. And then I'm multiplying that. Oh, that's not what just went in there, is it? Let me fix that. Undo, undo, undo. There we go. Times 4. There we go. So that's exactly what I wanted to convey to the calculator. So that looks good. Hit equals. And then notice we're being asked to round to the nearest tenth. So that's one place past the decimal point. So I'll look 2 places past. Since the second place is a 7, that means I'll round the 7 in the tenths place to 8. So A is equal to 1,322.8, and then that's grams. And then think about it. Does this make sense? This is decaying, so the amount that I start with is 2611, and the amount that I end up with is 1,322. So yes, this decreased. That makes sense. So I feel good about that answer. Let's take a look at another one. Okay, the number of bacteria in a certain population increases according to this continuous exponential growth model. With a growth rate parameter of 1.3% per hour, so notice this time it's a growth rate, so that will be positive. How many hours, okay, so it looks like we're looking for time, does it take for the size of the sample to double? Okay, so you'll see this a lot where we're talking about something doubling, or the example that we're going to look like next is half-life. So let's talk about how to think about this. So I'm going to jot down my exponential growth model. Okay, so I've already identified a couple of things, right? I know that R is going to be 1.3%. So that would be 0.013 if I convert that to a decimal. Remember, I'm going to move that decimal point over 2 places to the left. How many hours does it take? So I've already decided that I'm looking for T. And then all I know about what I'm starting with and what I'm ending up with is that this amount is going to double. And so it actually doesn't matter what you start with as long as what you end up with is twice that. And so make it easy on yourself. So when I'm deciding what do I start with, I'm going to pick an easy number. Let's just say 1. So if it doubles and I start with 1, I'll end up with 1 times 2 is 2. And so it really doesn't matter what numbers you put there because the ratio is always going to be the same. So I'm going to have 2 is equal to 1 times E to the 0.013, and then T is what I'm looking for. And so what I mean by that is the first thing I'm going to do before I try to get T by itself is I want to get the exponential expression by itself. So I would divide both sides by whatever this coefficient is. So if I divide both sides by 1, right, that is going to give me just 2. So 2 is equal to E to the 0.013T. So what I wanted to show you is like it doesn't matter if I had put a 2 here and then doubling 2 would be 4, because when I divide both sides, it's always going to divide out to 2. So that's why I usually just go with 1. Doubling 1 is 2. It keeps my numbers small and they're easy to work with, and that will work every time. So now, in order to get T by itself, I'm going to apply natural log to both sides so I can bring that exponent down using properties of exponents. So natural log to both sides allows me to bring that exponent down front. So this is natural log of 2, and now I could bring that exponent down is equal to 0.013 T. times the natural log of e. So remember, the natural log of e is equal to 1. So this just means I'm multiplying by 1. So I have the natural log of 2 is equal to 0.013t times 1. And then I'll divide both sides by 0.013 to get t by itself. So t is equal to natural log of 2 over 0.013. So let's go ahead and plug that into the calculator. So we've got natural log of 2, and then that whole thing has to get divided by. So I'm going to click to the outside of it before I hit divided by, because I don't want to divide 2 by 0.013. I want to divide the natural log of 2. So make sure what you see in the calculator is exactly what you see over here on your paper. So 0.013 equals. Okay, so let's see, we're rounding to the nearest hundredth. So when I look 2 places, that 100th place is a 1. So let's go over to the 3rd place is a 9. So that means I will change that 1 in the 100th place to a 2. So my final answer, rounded to the nearest 100th, is 53.32. Okay, last example, let's take a look at one with half-life. So I took this right from the homework so you would see exactly how it's asked and how we're going to approach this. So we've got this, and I might even say this wrong, Rutherfordium-265 is a radioactive substance that decays according to the following function, where y sub 0 is the initial amount present, right? So notice this model that we're given, it's the same one that we've been using, except they're using y instead of a. So y sub 0 is the initial amount, and y is the amount present at time t hours. So after this decay has occurred. So again, that's consistent with what we've been talking about. The model is given, so we're actually given the decay rate. Notice it's negative. And again, we're going to be looking for t, which is, so the question is find the half-life. So half-life of this Rutherfordium-265. So half-life is the amount of time it takes for half of the radioactive substance to decay. So whatever is present now, half will be present, half that amount will be present in the amount of time that we're looking for. So we're given this model. So we've got y is equal to y sub 0 e to the negative 0.0528t. So just like with the previous example where we were doubling, it doesn't matter what y sub 0 and y are as long as I'm following the question, right? So I always say, okay, let's say I start with 1. So if half will be present after this t amount of time, then y is 1/2. Okay, so we're already given the rate in the model, and then t is what we're looking for. So for y sub 0, I'm just going to put 1, and for y, I'm going to put 1/2, and then we have everything else. E to the negative 0.0528t. And we'll approach this exactly the same way, right? So if I divide both sides by 1, 1/2 divided by 1 is just 1/2. So let's go ahead and just take the natural log of both sides. So the natural log of 1/2, or you can rewrite that as 0.5, that might be easier to plug into the calculator, is equal to the natural log of e to the negative 0.0528t. Bring that exponent down. So natural log of 0.5 is equal to negative 0.0528 t times the natural log of e, which again we know is 1. Anything times 1 is itself, so I'm just going to cross that out. So as a last step, we'll divide both sides by this number. Okay, so my t, I'm going to approximate, let's see, it says to the nearest tenth. And so this is what I'm going to communicate to the calculator. Okay, so let's go over here. We've got the natural log of 0.5. And then remember, I'm going to divide that whole number. Like if I hit divide now, notice it's just going to divide 0.5 by whatever I enter. So you have to be really careful there, right? So you want to make sure you click on the outside of it before you hit divide. And then we'll enter negative 0.0528. And I'll hit equals. And that gives me, what are we rounding to again? The nearest tenth. So 13.1. And that's time in hours. Okay, and so then let's see, does that make sense? So if we start with, so that means it takes 13.1 hours for half of the initial amount of the substance to decay. So the half-life is 13.1 hours.